In this example, we are having a force tension at an angle, so we'll have to deal with the sine of the angle. So in this example, we just want to do forces of torque and the look at that first condition only. So we're going to draw a force vector downwards here, coming from the center of the books. And then somewhere there'll be the center of mass of this plank. We'll label it right there. Okay, that's good enough. And then we'll need to look at our force tension vector. We've got one going upward this way. And of course we have this direction here. Okay, so then we have force tension in the x direction and force tension in the y direction. And let's call this one force gravity 1, and this one over here force gravity 2. Now there will be a distance for each of these. If we want to call the distance for this one distance x, and for the second one we'll call it distance y. I'm just going to kind of label it over there because it'll get too confusing. So we'll just say the sum of all torques is equal to 0. These two torques will be negative and force tension y will be positive. So we're just going to go like this, equals a negative force gravity 1 multiplied by an x distance, a minus force gravity 2 multiplied by a y distance, okay, plus a force tension multiplied by the whole distance d again. All we got to do now is add the sine of the angle theta there. So whatever angle is here will then give us this angle here. And then force tension y is actually the perpendicular force that causes rotation upwards on this. But force tension y, of course, is force tension times sine of theta. Okay, and here's our theta here, which represents our 30 degrees in this particular case. So that's why we end up with force tension times d times sine theta. And then we really are finding the force tension value here in this case. Okay, now there is a force tension x pushing this way. And if we look at this point P, force tension x is the one pushing the board into this pole. So there would be a opposing force going backwards right there, equal and opposite. Let's call that force pull x. So force pull x is going to be equal to force tension x. So I'll find that this member gets compressed, whereas this measure here gets stretched. So there's tension force on this one and compression force on this. If you remember our bridge that we built this year, those are the two kinds of forces on a bridge, tension force and compression. Okay, moving on, let's do center of gravity calculations. So let's say we put an origin at this location, and we have two objects that are together, and we're envisioning this as a square and this one as a rectangle. And we want to find the center of mass of the object. So the way we do that is we'll find a center of mass of this one will exist right in the middle, and the center of mass will exist for this one here as well. Okay, so let's keep this simple here today. Let's call that 0, and we'll call this 2, and we'll call this 4 here. Okay, and we'll give this one, let's give it 4 kilograms. And we'll give this one 2 kilograms. Okay, so, and then of course this would be 2 over here as well. Okay, and then this would be up 1. Okay, so to get the center of mass of this, the coordinate for this one here is going to be 1, 1. That's the center of this box. Okay, now the coordinate of this one here is 0.5 in the y, because it's 1 high this way, but it's 3. So if you look at the number line, this would be 1, that's 2, this is 3, and that's 4. And this right here is 0.5. So the coordinate for this one would be 3, 0.5. So if I want to get the center of mass of this whole object, then I'm going to multiply. Let's do center of gravity in the x direction. That's going to equal 4 kilograms multiplied by 1 plus 2 kilograms multiplied by 3. Okay, and that's going to be all divided by 4 plus 2. Okay, and then center of gravity in the y direction is going to equal 4 times 1 plus 2 times 0.5, all divided by 4 plus 2. And that'll come out as an ordered pair. We'll have an x and a y ordered pair for that. So that's how we do center of gravity or center of rotation calculation. You multiply the value of masses multiplied by their x coordinates and by the y coordinates, and you write separate values for those. All right, our final example in this video is going to be on gear ratios and mechanical advantage. So let's say I'm spinning this gear down here, and then it's going to cause this one to spin. Of course, this one has to spin faster because it's smaller to keep up with it. So mechanical advantage for the system is going to be equal to the radius of the gear that we're actually physically starting to move divided by the radius of the gear that's moving because of the first gear. So our mechanical advantage in this case is going to be 2.0. So what that means is if I'm spinning this gear here, let's say I'm spinning it at an omega equal to 2.5 rads per second. This gear here then, I'll call it W1. W2 has to be spinning twice as fast, so 5.0, and that's rads per second. So it's a mechanical advantage because for every one rotation of this gear, we get twice the amount of rotations of this gear. But remember, you get nothing for free in physics. I'm pushing on this gear. I have to push with a larger force to make that one move. And you're probably familiar with that when riding your bicycle. When you get a larger gear on the first pedal, it's harder to push down on those gears. So again, nothing for free in physics, but that's how gear ratios work.